Okay, so today I want to start a new section on integral representations, and in particular integral representations of solutions to differential equations. So, we spent a little bit of time talking about the properties of differential equations, and in particular differential equations with on the complex plane. And this has really given us the tools that we need to try and understand how to solve these differential equations in a more general way than you're probably used to. So as part of our learning goals for today, I want to introduce the idea of solving a differential equation using integral representations. Well, okay, so I'm being a little bit glib here. I don't actually plan on solving many of these differential equations. What I want to do is show you that you can write an expression for the solution of the differential equation without actually getting a formal solution. But sometimes this integral representation of the solution, in fact, is enough for you to deduce many of the properties of the solution without actually solving the differential equation. And again, the go-to example here would be the logistic equation that you would have learned about probably in first year already. Basically, x dot is x times 1 minus x. It describes population growth in a constrained environment, and it describes the way rumors spread, etc. In some instances, it describes, for example, how viruses propagate in a population of fixed size. The idea there is that just by looking at that differential equation and studying the differential equation as a dynamical system with two fixed points at x equals 0 and x equals 1, you would be able to write down, you'd be able to guess the properties of that solution without actually solving the differential equation. The equation itself can be solved. It can be solved because it's a separable differential equation in x, and you can use the method of partial fractions to solve it. But that's not the point. The point is you can actually read off the properties of the solution. In fact, you can read off that it will have this characteristic S-shaped curve, that it will asymptote to 1, that it has a turning point, a point of inflection. All of these properties of the solution you can read off without actually solving the differential equation. Of course, the logistic equation is a fairly trivial example of the kinds of equations we'll be solving. We're more interested in differential equations that feature in mathematical physics, in quantum field theory, and general relativity, and just mathematical physics more generally. So that's going to be our philosophy. Can we solve these differential equations? Can we find expressions for the solution of differential equations without actually solving the DE itself? Now, in a general first course in differential equations, at UCT, we would call this MAM 1043 or 1044, or MAM 1000, the latter part of MAM 1000. You will have learned that you can solve, in a rather general way, differential equations by power series expansions. The problem with power series expansions is, even though they are a very powerful method for solving differential equations, basically you write down a general power series expansion for the solution, plug it into the differential equation, which gives you constraints on the coefficients, and then hope you can resum to get a closed form expression from the solution. But even if you can't, you can certainly deduce a whole bunch of things about the solution of the differential equation from this power series expansion. But the problem with these power series expansions, and this is true of any series solution to pretty much anything, is that the solution is only good inside a particular radius of convergence. And this radius of convergence is typically small. So, just because you can write down a power series solution doesn't necessarily mean that it's particularly good for the entire domain of the differential equation that you're trying to solve. And so you need to establish where it's good and what its radius of convergence is. And if you want to extend outside of that radius of convergence, then typically you need to, what you would call in complex variable theory, analytically continue the solution. However, there is a rather powerful method of constructing solutions of differential equations that are, instead of being based on power series solutions, and if you keep in mind that power series solution is a method of Taylor expansions, and Taylor expansions involves working out derivatives, there's a rather powerful alternative involving integrals, and this is the method of integral representations, and it's based essentially on the idea of integral transforms. So just by way of what we're trying to do here, let me note that integral transforms can yield integral representations that automatically incorporate analytic solutions, analytic continuations. So we would like, in this section, to use integral transforms to give integral representations of the solutions to differential equations. Okay, that's the goal of this section. Any questions? So the main idea behind this method is so suppose I have a differential equation in some variable u of z. So unless I specifically say so, everything we're going to be talking about here has to do with differential equations on the complex plane. So my independent variable is going to be z. Z is going to be some variable in the complex plane. And the functions that I'm interested in, the solutions of the differential equation, are functions of this z. So the main idea here is that we want to express the solution of a differential equation in terms of an integral. Yeah, we want to express the solution of a differential equation of some dE as an integral of the form u of z equal to the integral over some contour c of k of z and some parameter t, v of t dt, for some contour c in the complex plane. And we want to, integral kernel k of zt in such a way that the differential equation becomes easier to handle. So this is some contour. In C, this guy here is known as an integral kernel. And it's going to be the crux of what we're planning on doing. And the function v is some unknown function to be determined. This is not as unfamiliar as it might seem, because you might have seen this before. In fact, for particular choices of kernel, this is nothing but a Fourier integral transform or a Laplace integral transform. So some well-known kernels are, for example, if I choose k of x and y equal to e to the I xy, this is nothing but the Fourier kernel. Which you will recall, because whenever you do an integral transform, a Fourier transform, you always go function times e to the I kx, integrating over some variable, either k or x. On the other hand, if we choose k of, let's say, x and y to be the real exponential, e to the minus x times y, then this corresponds to the Laplace kernel. So if you're familiar with Laplace transforms, as I hope you are, you will recognize this exponential whenever you do a Laplace transform. Right. So this idea of integral transforms and the kernel of an integral transform should not be an unfamiliar one. We're just going to be using them in a far more sophisticated way. Any questions?
Could you go back up, Jeff? I couldn't get the last equation from the last page.
Is that better?
Yeah.
Can I move back?
1 more second.
Okay.
Yeah.
All right. Very good. So that's the Fourier kernel and Laplace kernel, respectively. And if you remember, the point of solving differential equations using Fourier methods or Laplace methods, you took a differential equation in, let's say, X space, did a Fourier or Laplace transform, converted it to an equation in T space or K space. In the physics nomenclature, you would have gone from position space to momentum space. And the effect was to reduce the differential equation, typically, to an algebraic one, which you could then solve quite trivially. Because ideally, you didn't want to have to solve differential equations. So when you went from X space to K space, you converted your differential equation into an algebraic equation, and you could solve the algebraic equation using, basically algebraic methods. There, you were solving an algebraic equation for this function v of t. So the function u of z would generally solve a differential equation. When we introduce the integral kernel, we will get an equation for this function v of t, and we would pray that the equation for v of t was at least simpler than the original equation for u of z. If we're lucky and we choose the kernel, this guy, appropriately enough, then we can convert the differential equation in u to an algebraic equation in v. And if we can do that, then we solve for this algebraic equation, plug it back in here, and we have an expression for u of z. Is my method clear?
Yes.
Good. So our goal here will be to generalize this argument and apply it to derive integral representations of some frequently encountered differential equations in physics. So let's write that down. Our goal will be to derive integral representations to some frequently encountered DEs in physics, physical problems. Okay, very good. And this is, then let's go back to our learning goals. So we want to introduce the idea of integral kernels, which I just did. The example that we're going to be working with primarily is an equation that one encounters in the physics of the hydrogen atom, for example, called the hypergeometric equation. And then we'll do a particular example of a quantum mechanical particle moving in a particular potential called the Purcell-Teller potential. And this is a useful example because we will revisit it a little later and try and solve it using another method, the method of factorization of differential operators. And I'll show you how this Purcell-Teller potential can be mapped to a almost trivial problem of a particle in a square well. Okay, from the perspective of mathematicians, these are just differential equations that we want to try and solve. From the perspective of physicists, these kinds of differential equations occur very, very frequently in quantum mechanics problems, sometimes in classical mechanics, classical celestial mechanical problems, etc. Okay, so toward the end of solving these equations in terms of integral representations, let's try and write down a formal method first, and then I'll expand on this formal method. I'll unpack it a little bit in a particular example. So I want to consider a differential operator in some independent variable z, and I'm going to label it by L subscript z. So let's consider the differential operator So I'm not so much concerned about differential equations per se. I am concerned about the operators that show up in these differential equations. So everything's going to be phrased in terms of operators and operator calculus. So consider the differential operator in the variable z, and I'm going to call this thing L sub z. Okay. And we want to solve an equation of the form L z acting on some function u of z equal to 0. So Lz could be d by dz, d2 by dz squared, 6 d2 by dz squared plus 3 dz dd by plus 3 d by dz acting on this function u equals 0. And I don't really care about the differential equations by themselves. I am interested in the fact that I can write this equation in the form Lz acting on u equals 0. So now let's assume that we can take the expansion that we wrote down for u, and we'll stick it into the differential equation. So substituting u of z equal to the integral over c of k of zt v of t dt into the equation. We'll find the following. Notice that L is an operator on Z, and the only thing that depends on, that has any Z dependence in this ansatz for U is the kernel K of Z. So L is only going to act on that. So I can take it into the integral, which is an integral over T. Lz acts on the kernel of Z T and not on V of T dt. And of course, Lz acting on 0 is 0. Okay, and here's the crux. Suppose I can find another operator. So this is the main key point. Suppose that we can find an operator M T such that, so again, I'm labeling the thing that the operator acts with respect to as a subscript. So Lz was a differential operator in Z. Mt is going to be a differential operator in T. And I'm going to define this Mt such that the following is true. LZ acting on K of ZT is the same thing as MT acting on K of Z and T. So suppose I can find such an operator. All right. And such an operator will exist if the operation of integrating by parts is valid. So this is my constraint condition on the operator, that LZ acting on the kernel is the same as MT acting on the kernel. So suppose there exists such a function. Okay. So then I go back to my differential equation. Then zero, which was the right-hand side, was LZ of U. That's my differential equation. That was equal to the integral over C of LZ acting on the kernel times V of T dt. And we just said that by our assumption, we're going to replace this LZ, sorry, we're going to replace the LZ acting on the kernel with this new operator, which I don't know what the operator is yet. I'm going to need to work that out, but I'm just assuming that it exists. But I'm going to replace LZ with this new operator acting with respect to T. Remember, the kernel is a function of both Z and the parameter T, the dummy variable of integration. So what if I can do that? Well, if I can do that, then I can also integrate by parts. And if I integrate by parts, remember, MT is a differential operator. So when I integrate by parts, I throw the action of any derivatives acting on the kernel onto what's left in the integrand, which is V of T. And then I gather all my terms and I call that the adjoint of MT. In other words, when I integrate by parts, I get the kernel K of X, sorry, K of Z and T. And what's left is MT dagger by definition of what the adjoint is, acting on V of T dt. But this is not all, because whenever I do an integration by parts, I will always end up with some boundary contribution, which I'm going to call Q of K and V. And this thing is typically evaluated on the boundary of the curve it's typically evaluated on the boundary, not typically, it's always evaluated on the boundary of the curve, which following standard convention will denote by partial C. Are we clear?
I wanted to ask, when we do integration by parts, we normally pick up a negative in front of the integral. Does that just get absorbed into the kernel or something like that?
Yep. It gets absorbed into this term here. So any negative signs gets absorbed into what I call the adjoint operator.
Right. Thank you.
Okay.
Sorry, Ralph.
Yeah.
Yeah, just to check on the first line there, when we take our differential operator M on T, why does it only act on K and not on the product of K and V?
Because, wait, I'm sorry, which one are we talking about?
The first line.
Why does MT only act on K?
Yes.
By definition.
And not on the product of K and V. Oh, so it's by definition.
Yeah, you might also be asking do you get why L only acts on K and not the product?
X on K, yes. Yes, I do understand that.
Right. Then my definition of what M is this here. That LZ acting just on K is MT acting on K. That's my definition.
Oh, okay.
So then if I go back to this
okay.
equation, the reason why it's not acting on the product is because I defined it to be acting just on K.
Oh, okay. Thanks.
Okay. This here is the adjoint operator. Of M, and the way I get it is by integration by parts. So what we've done here is simply integrate by parts. Okay, very good. Then my statement is that the original differential equation is solved if I can find, and I'm not always guaranteed that I can, if we can find some function v of t such that the whole right-hand side of this expression here is also equal to 0. Okay, so again, I started off with this operator, LZ acting on U. I know that LZ acting on U is LZ acting on K times V integrated with respect to T over some contour. I assume that I can find this M such that LZ acting on the kernel is the same as MT acting on the kernel. I integrate by parts, so I get this expression. And this expression is equal to 0. In other words, it solves this differential equation only if two things are true. One is because if I assume that the kernel vanishes, then the whole thing's trivially true, which I don't want to have. I want to have some non-trivial statement here. But I can also ensure that the first term vanishes if MT dagger acting on V is equal to 0. And Q, this boundary term, is also equal to 0. So I want to be able to find some function v of t that satisfies two equations. One is that MT dagger acting on v of t vanish. And two, that this boundary term q of k and v, whatever it is, which I'll get from integration by parts, also vanish. Okay. Well, this equation, the first one, is a differential equation, typically. Okay? Not always, depending on the kernel. It can sometimes be an algebraic equation, like with the Fourier kernel. But typically, it's going to be a differential equation. Now, if the differential equation for M acting on V is as or more difficult than the original equation, then there's very little point in this whole exercise. So essentially, this whole story boils down to a clever choice of the integral kernel. That's the whole point of this game. Okay. So this is a differential equation. That we would hope is simpler than the original one. And if it's not, then we've essentially wasted our time and we've got to find another integral kernel. Okay, any questions? No? All right. So, as I've said, this whole procedure comes down to picking a suitable integral kernel. In the same way that if I gave you some differential equation in, let's say, your third year course of mathematical physics, and you had to solve the equation using the method of Laplace transforms or the method of Fourier transforms, which you choose would depend very much on the differential equation. So the choice of the kernel, Laplace or Fourier kernel, and therefore Laplace or Fourier method in solving the differential equation, really comes down to the structure of the differential operator. Okay, so this is just saying again, the choice of the kernel that you will choose to solve a particular problem is dictated by the form of the original differential operator. So let's illustrate these formal ideas by a particular example. And the particular example I want to use is what's called the hypergeometric. So as an example, let's choose the hypergeometric differential operator. And I'll show you why it's called the hypergeometric operator in a little bit. But for now, let me just write down its form. Lz, the hypergeometric operator, is z times 1 minus z times the second derivative operator, d2 by dz squared, plus some gamma minus alpha plus beta plus 1, where alpha, beta, and gamma are parameters. So depending on the particular differential operator we're looking at, there's a particular choice of alpha, beta, and gamma. And these form the coefficients of the first derivative operator, d by dz, minus some constant piece, alpha, beta, like that. Okay, so this is what's known as the hypergeometric operator. And this is the operator we want to study right now and use it to illustrate this method of solutions of differential equations. In this case, the differential equation we're going to be concerned with is the hypergeometric equation, which is found when you try to, which is one place you could find it is when you try to solve certain quantum mechanics problems and variants thereof, for example. And the first stop in our algorithm to solve this problem using the method of integral representations is the choice of kernel. Here, the choice of kernel is going to be dictated by the fact that the coefficients of the differential operator, the coefficients of the derivative operators in this expression are polynomials in Z. And since they're polynomials in Z, we will choose what's called the Euler kernel. So since the coefficients are polynomial, we're going to choose the so-called Euler kernel K of Z T equal to Z minus T to the S for some S. Okay. So now let's follow through with our method and see where we get. So to do that, we need to act on this Euler kernel with the hypergeometric operator. Everybody copy this down? Can I go to the next page?
1 second, 1 second.
Okay. Just let me know when I can.
Now you can.
Okay,
Yes, you can. Yeah.
good. So there are three parts to this. So acting with the hypergeometric operator on this kernel, Z of T. Find the following. First one is the term that looks like Z times 1 minus Z. Second derivative squared acting on Z minus T to the S. Two derivatives pulls down a factor of S and S minus 1. So this will give me an S times S minus 1 times Z minus Z squared, where I've just multiplied through the Z in that expression, times Z minus T to the S minus 2. That's the first term. The second term, gamma minus alpha plus beta minus, did I say plus or minus? What did I say here? Plus 1. Plus 1. Times d by dz acting on Z minus T to the S is just S times gamma minus alpha plus beta plus 1 times Z minus T times Z minus T to the S minus 2. The reason I did this is because I want to try and make sure that I'm comparing like with like. So this is a z minus t to the s minus 2. This has a z minus t to the s minus 2. And to get there, I need to pull out this factor of z minus t. And then finally, I have the constant piece, and the constant piece will have a alpha beta times z minus t to the s, which is alpha beta z minus t squared times z minus t to the s minus 2. Okay, so then what I can do is pull all these pieces together and group them in an appropriate way. So if I act with LZ on the kernel, then I group terms I'm going to group terms now in z minus t to the s minus 2 and z squared, z, and constant pieces. Then the expression that I get will look like this. Okay, so powers of z will have, coefficient of z squared will look like minus s to the s minus 1 minus s times alpha plus beta plus 1 minus alpha beta plus power of z, the linear term, will have an s times s minus 1 plus s gamma plus s times alpha plus beta, can I put that there, plus 1 times t minus, plus 2 alpha beta t. Okay, close brackets there. Minus gamma st and minus alpha beta t squared. And all of this multiplies z minus t to the s minus 2. So that's the action of LZ on the operator. On the kernel, on the Euler kernel. So then the question becomes, given this horrible looking thing, how do we even begin to choose this operator MT? Okay. And this is always the case. If you can find patterns, identify those patterns, and they will lead you out of the quagmire. In this case, we notice that there's a certain symmetry satisfied by the kernel. So you're probably going to complain after this that this was a very special case. And I don't disagree. This is a very special case. And in fact, as is true of most of these functions and differential equations in mathematical physics, nature seems to prefer the very special cases to the general case. So it's not such a big deal that this is a special case. And many of the problems that we identify in nature turn out to be such special cases. So how do we choose this operator MT? Well, the first thing is we notice that there's a symmetry satisfied by the original, by the Euler kernel. And the symmetry is that k of z and t, which remember was z minus t to the s, is just -1 to the s times k of t and z. So exchanging t and z comes with a factor of -1 to the s. So this is interesting because it seems to suggest that this operator mt should be of the same form as Lz, except perhaps for an exchange in z and t. Okay. So this suggests that we should look for an operator of the same form as Lz, except for z and t interchanged. I still don't know what it is, but I can now make an educated guess. So let's guess then that mt is the operator p of t d2 by dt squared plus, in fact, I'm going to need two of these guys. So let's call it p2 of t, the two corresponding to the second order derivative, plus p1 of t d by dt. And in principle, I can add a p naught of t, but I'm going to see if I can get away with not doing that. So let's take, if it doesn't work, it doesn't work, and we'll go back to the drawing board. But let's see if we can start with this as a guess. So no constant term, just in the hope of having some simpler operator to work with. Okay. Now we want to apply this to the differential operator. I'm not going to do it today, but I'm going to tell you what the strategy is. And we'll pick up again on Thursday. But here's my guess for what my operator is going to look like. And my strategy is going to be apply this operator to the kernel. And remember, by definition, I want that Lz acting on the kernel must be the same as this guy, mt acting on the kernel. So this is going to give me a set of algebraic equations for the coefficients p1 and p2, which I'm going to use to solve for p1 and p2 in terms of the original parameters, alpha, beta, and gamma. And hopefully it'll nail down s as well, which ought to give me an expression for what this mt is. Then we're going to plug it back, do an integration by parts, and end up with a differential equation for v, which is hopefully going to be simpler to solve than the original differential equation. Okay, so that's the goal here. And once we have the simpler differential equation, I'll show you how we can solve it next time. Any questions?
Jeff, I have a bit of a question with regards to notice that k of z, z comma t is equal to -1 to the s. K of, oh, is there something to do with the variables being flipped in there? When the order.
Well, are you asking why k of zt is -1 to the s k of tz?
Yeah.
Well, because K of ZT.
Oh no! Oh, okay. I get it. Because you when you flip the T and Z in the
Correct.
definition. Okay. Thanks.
Okay. Any other questions? All right. So if not, let's stop there. So next time, again, we're going to follow through this strategy, try and nail down the coefficients P1 and P2, and use that to get an expression for M. Then subsequently get a differential equation for V. Hopefully, we can solve this differential equation for V. And if we can, or at least put down some conditions on alpha, beta, and gamma, we can then write down an integral representation for the solution of the hypergeometric equation. Okay. All right. Thanks, everybody. I'll see you again on Thursday.